this proxy, the buffer as mg1 queue. So basically, we assume this arrival to the proxy is post on arrival, and this the service time is general. So here you can think about this. If the so what is the service time for this for this proxy to a message? What is the service time? So service time actually is there's two situations. But so if the packet, the real message, we talk about real message getting into the buffer, when you arrive, if the buffer is empty, which means this message will be delivered at the next time point. Right? So here we use constant rate transmission. Right? So here the waiting time, the average waiting time is half of this interval. Right? The transmission, but the reverse of this, inverse of this constant rate. Right? So in that case, we consider this as a service time, although you don't really do any processing, but it's virtually the same as the service time. But when this message arrives at the buffer is now there's some other real event there, but you cannot be delivered at this moment. So after a while, the packets move towards the head of this buffer. Right? So in that case, when you are served, you get into the processor or this proxy. The waiting time is exactly one time interval, right? Because once you get the last one, and you're the next one to serve, you have to wait for one interval to be delivered. So that's the time. So the reason we have modeled this service time. The average service time is one case is when you arrive at this buffer. The buffer is empty, and this is the average average service time. And another case is when this buffer is not empty. So in this case, the service time is this interval for the buffer interval. And then we can derive this average sojourn time. Right? So when this real message arrives at this the proxy and when it is delivered, so you can calculate this the entire time. And we did some the simulation to validate this model. Seems very close to each other, and also we did some simulation to find what is the maximum queue size, the buffer size, because if you have too many real events in this buffer, then what you should do, right? So if it's already full, but you need to drop some of them. Right? So our question is what should we set as the buffer size? If we know the maximum size, then we can set appropriately the buffer size. Right? So then we will not drop the real events. Okay, so that's the part of the first scheme. And the second scheme is a simple extension of the first one. So our motivation here is if you have multiple proxies and every proxy directly send this to base station, and you may still have lots of dummy message from the output of a proxy node, because you have to even there's no real message, you still have to keep this constant rate. Right? So our idea is okay. Now why not we use the hierarchy? Right? So we have from one proxy the output to another proxy. So in that way you may filter more dummy traffic. So this is the basic idea. And so in this way you can reduce the network traffic, and but the others. Actually, let's see the overall performance here. So in this case, we showed we choose different number of proxies, and this is the traffic overhead. So this is the one we use the proxy-based scheme. Another one is here we have this two-level proxies, and this green one is when you have three-level proxies. So you can see this overall network traffic is becoming lower than the PFS scheme. It shows that this kind of hierarchical structure will help to filter the more dummy traffic. And of course, now you have more, because every new event you have to go through multiple proxies. And in every proxy, there's a waiting time, right? So the overall, this waiting time will be larger. The latency will be larger. So this is a trade-off. So we should here use some simulation to evaluate these schemes and these other parameters. Let me see if okay. Okay, so we simulated two scenarios. One is the high rate real event case. Another is low rate. So basically, for the real event, we cannot control like what is the the actual rate. So we want to use the one case is very high rate and another is low rate. And this is the time interval for the proxy to send out the messages, and the buffer size here is 10. And this is the result on the high rate real events. You can see here the first one is the baseline scheme, which means you don't do any filtering. So every packet is forwarded to the base station. But here we don't do any reliability guarantee. So best effort delivery. So if the packet is lost, then it's lost. So I mean, so this is a fair comparison because it's not just for their scheme. For our cases, we don't also do any kind of reliability service. So you can see that in that case, the overhead in the baseline scheme is much higher than in our scheme. Here again, you can see here TFS2. Here you use the two levels. The two levels, you see the overhead is a little bit smaller even. And for the delivery ratio here, you can see that the baseline scheme is much lower than in our case. So here the x-axis is the mean for the bogus message transmission interval. So in every source you have this you have the mean for message transmission. So in this case, the reason it is in the baseline scheme is slower because of the congestion problem. Because so many packets, once they are closer to the base station, congestion happens, so they are dropped. So in our case, because you have much less packets to send, so the delivery ratio is much higher. And here you can see this delay in our scheme. This is TFS2, right? So 2 levels, and the delay is highest. And this is the PFS, just one level proxy. So it's in the middle. And in the baseline scheme now, so it's doing better. The delay is lower than in our case. If you can see this because every node just forward this, try your best to forward this, receive the message as soon as possible. But again, here I should point out this, because it's a trade-off. Right? So now if you do this way, you have more packets to send, and the packet delivery ratio will be lower, and also the overhead is also larger. And we also did a simulation for low rate real event case, so the result is similar. Okay, so this is the conclusion of this talk, and I described these two techniques. One is to provide statistically strong source anonymity for dummy traffic generation, and also we have the optimization schemes to try to find the number of proxies and where to place them to try to drop more dummy traffic. And in future work, we also consider key anonymity scheme and the hiding distribution. So the point here is that for our first scheme, in the first scheme, the performance of the first scheme actually will reduce if you have many packets to send, but many real events to send. But if there's just one real event to send, then you can perfectly hide it in this all these dummies. But if you have so many real ones to send, then you have to do recovery this interval. So and after certain real events happen, then you have to increase that, right? So in that case, it's not an efficient scheme. So what we are thinking about is, for the heavy traffic, in the high rate case, we can actually use a key anonymity scheme, but use our previous technique as the way to generate a notification message. So the idea is, so in the normal case, and our protocol will be running there, and there will be very low rate. It is only used to